Hi there. In this episode, I'm going to restore an old Knight vacuum tube voltmeter. Now you're probably thinking to yourself, why do you want to waste your time with an old vacuum tube voltmeter when all the new digital multimeters have high impedance input and, they're a dime a dozen? Well, it's actually kind of handy to have a meter that has a high impedance input with analog movement on the bench. Say you're working on an old receiver and you're peaking up the RF section and you want to monitor the AVC or AGC voltage. It's much nicer to watch an analog meter rise and peak and then maybe fall off so you can find that peak than it is to watch digits count up, kind of even off, and then start to count back down again. This meter reads up to 1500 volts DC. It reads RMS voltage, reads 4000 volts peak to peak. It reads ohms. They're incredibly resilient meters. You can just about not destroy these things. It plugs into the wall, so you're basically never buying batteries. They do have one battery inside, but it takes a lot to make that thing go dead. Some of these old voltmeters have the original battery inside them, an old mercury cell, a 1.35 volt mercury cell. So this one here, I don't know if it has the original cell in it or not, or what's going on. I haven't opened this up yet. But there's just a couple of reasons why you'd probably want to have one of these things on the bench. Now, you can usually pick these things up for almost free at your local ham radio swap meet or, any kind of online auctions or something like that. They usually go for very, very cheap, and they're very handy to have. Now, this one here is kind of desirable for me because it has a really nice big meter on the face. I have one other vacuum tube voltmeter with just a ginormous meter. It's an old ICO. It's, probably quite a bit larger than the meter on this one. And I might restore that one down the road too. That's a really neat looking voltmeter. But it is kind of nice to have a nice big meter and a nice big movement so that when you're peaking up those voltages and stuff, it's very clear and easy to see. It's either that, or in some of the receivers you can actually use the eye when you're peaking up the RF. You can watch the eye close, like in the Stromberg-Carlson video. That was a really good representation of using the eye to peak up the RF section in the radio. At any rate, let's get into the restoration of this vacuum tube voltmeter, and just like in all the other videos, sit back and relax and follow along with me, and we'll go through this piece by piece. I haven't had this apart. I don't know what's inside it, so you know as much as I do, really. It's just sitting here on the bench, ready to go. So let's get into the video and get going. I'm now ready to open this up and get inside to see what I have to do to restore this. So in order to go inside this, I just have to remove these 4 screws here. And then this whole face should just come out like this. Now, there are a couple of screws on the side which kind of mount this to the bracket, and you can see the little calibration holes here. But I might have to remove this, and then of course there's the same one on the other side here. Yeah, that's if the chassis hangs up when I'm trying to remove it. But other than that, it looks pretty straightforward, just 4 screws, and this should come out. The power cord comes through the back side here. This is looking a little bit gross. There's some corrosion on here. It looks like there's some mud on it. So the cord itself is in really good condition. It's nice and soft still, and there's no cuts or anything, so this might just be able to be cleaned up and left on the unit. So I'll remove this from the case and we'll check out what's inside. I've removed all the screws from the face. You can see here, 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 and here. And it comes apart relatively easy. Just kind of grab the knobs like that and lift the front of it out. Now you'll see here in the back there's a rubber grommet, and it's tight around the cord, so what you're going to have to do is pull the cord through the rubber grommet and then kind of move the case out of the way so that you can get inside and service this VOM rather easily. Now, a lot of them are like this. They have this kind of a tight grommet around the cord. If you're going to replace the cord, of course you can remove it from inside, and then you've got all the freedom in the world to move this thing wherever on the bench. But even like this, if you move the case out of the way, it gives you quite a bit of free area, and nothing kind of binds up on these nuts in the side here. They have a little battery door on the bottom of this Knight here. I don't know if you can see that. There's a little battery door here, so on the bottom of this is the battery that you have to change for the ohms meter. And somebody has replaced this, obviously, because that's a Duracell battery and it's looking rather new. So, in the next scene here, we'll go into it and I'll explain how this actually works. We're now inside the vacuum tube voltmeter, and we can immediately see the 2 vacuum tubes right here. So this is a 6AL5 right here. It's a cute little 7-pin tube. There's 2 diodes inside this one glass case. That's really all this tube does. It's just 2 completely separate diodes in here. This is a dual triode tube in this glass case here. And what that means is if you wanted to look at this through, say, solid state eyes, or you wanted to compare this to a modern device, you could picture this as 2 completely independent N-channel FETs inside of one glass case. So this tube here is operating in a bridge circuit, And this tube here is an AC full wave peak-to-peak rectifier for doing the AC measurements on this meter. Now, if you have an older vacuum tube voltmeter, chances are it has a 6SN7 in it, which is an octal tube. It's a much larger tube. And of course, it'll be put together a little bit differently. So it'd have a 6SN7 in place of this 12AU7, and it would have a 6H6 in place of this 6AL5. Now, the 6H6 is a small little metal tube, and basically the same function as both of these tubes, just larger case. As time goes on, things are getting smaller, vacuum tubes are shrinking up, and you know, this particular era is where we're in right now. So this bridge circuit here is always in front of the meter, and in most vacuum tube voltmeters they always are. So this tube actually protects the movement of this meter. So if you make any gross over voltage measurements with this thing, this vacuum tube will protect this meter. So very rarely do you actually find an open movement in a meter. If you do, it's usually from some operator error, some guy poking around in here, shorting things out with a screwdriver or something like that. Usually the meter is really, really well protected by the vacuum tube. So what happens in this, just really simply and quite quickly how this works is, when you feed a voltage from the probe into this jack in the front here, what happens is this tube goes out of balance because it's in a bridge circuit, so it's got a balance, it's sitting at a balance, and when you apply that voltage, it brings it out of balance, and when that goes out of balance, the needle goes up because one particular part of the tube is at a higher potential than the other, and then of course you get a voltage difference, and that drives the needle upwards. And I'll show you a schematic here in just a little bit, and I'll explain how that works. This is just an AC peak-to-peak rectifier. And so how that works is for AC measurements on this meter, the AC of course goes in the same little jack here, and it needs to get rectified, and that's what this tube does. And it goes from this rectification into the bridge circuit again, and then from the bridge circuit into the meter. So ohms measurement, same kind of idea. It goes through a battery that's mounted on the bottom here. You can see this is a newer battery. Somebody's been in here before I've owned this and replaced the battery, so there's a very good chance that this thing was, you know, in service not too long ago. So the battery clip is kind of corroded. That'll need to get cleaned up. But how this works here is this battery is just for the ohms readings of this meter. So when you have a resistor, of course it's not, you know, it doesn't have any voltage across it, right? So what this does is this puts voltage through the resistor at the end of the probe, and then it goes back into the meter. And then of course it goes through a bunch of precision resistors in the switching here, and it goes back into the bridge circuit again, and then of course the bridge circuit is in front of the meter, and then of course bridge goes a little bit out of balance, and you know, the meter comes up. Pretty simple. So on the back here, you can see there's no wax caps, so this is going to be a relatively straightforward rebuild. These are ceramic disc capacitors, and they don't need to get changed. These things very, very rarely fail. So we have these here and these here, no problems whatsoever. We're not going to have to change those capacitors. This electrolytic here will have to go. If you open up your voltmeter and you look at the electrolytic and test it and it seems to be fine, don't take any chances. These things are cheap. They gotta go. They're out of there. Don't waste your time in reforming them, because if you reform this thing and you leave the room, one day you're going to find that the transformer is going to be reformed into a charcoal briquette. So these things are so cheap nowadays. This is what is it, 20 microfarads at 200 volts DC. Now in this particular unit, this is not a very particular value. This is just half-wave rectification on the actual secondary side of this little isolation transformer here, and it's just filtering half-wave rectification. So like this is 20 mics. You could, you know, comfortably replace this with a 33 or a 47. I wouldn't go much higher than 47, but you know, that would be absolutely fine. There's a solid state diode right here, and this is just for filtering the half-wave rectification on the other side here. That's all. So not much to do really in this. Spray the switches with contact cleaner, maybe spray the VRs, move the VRs around a little bit. I'm going to change this electrolytic cap with a modern electrolytic cap and get rid of this. Maybe check some of the resistance values in the bridge, just make sure they're okay. I'll test the tubes and see that the tubes are okay. And at that point, you're almost pretty much ready to put this thing back into service again, of course, and check and change the battery in the bottom for the ohm settings. One other little thing before I go. This is an isolation transformer right here, and this is also the heater transformer for the two vacuum tubes here. So what this does is this isolates the line cord, which is, you know, the cord, this black cord that's running in here. This runs right into this transformer, and then the secondary side, this is like almost a one-to-one transformer. So on the secondary side, we have pretty much the same voltage that's on this line cord, but there is absolutely no connection between the primary and the secondary. If there was, you would have a very, very dangerous device. So on the secondary side, the the high voltage that comes out of here will be roughly the same voltage as that's coming through the line cord, and it goes into this rectifier and just gets filtered by this cap, and we have, you know, clean DC at that point. You know, it'll be lower current, much lower current, because this is, you know, a very small transformer, but still nonetheless the voltages that come out of this transformer are still dangerous. So if you're, you know, playing with any kind of vacuum tube gear, you really need to understand that vacuum tubes run at much higher voltages than transistors and MOSFETs do in most cases. So you got to be very, very careful in these units. If you're not familiar with vacuum tube equipment, I would suggest that you study it before you actually do anything or go into any of this kind of gear, because you can really buzz yourself, and if you're really not careful, you could even kill yourself in this stuff. So you're doing all this stuff at your own risk. Just take care if you're going to fool around with anything with vacuum tubes or anything with electronics in it that plugs into the wall or that has any kind of high voltage in it. So on the downside, or the secondary side here, we have, say, like around 120, probably 125 volts, something like that, coming out into the rectification stack, again fully isolated from this. And we also have the heater supply for the two vacuum tubes here. So the 12AU7 and the 6AL5 both have 6-volt filaments in them. So the 12AU7 is a center tapped filament, so you can get two 6.3 volt filaments in this, and that's how they've got this hooked up. And then here in the 6AL5 right here, we've got the filaments, of course, go running over to this because it's just 6AL5, right? This, you know, 6-volt filament. So we can see that one filament pin is tied to the ground here, and we can see the other one is running over to here. And then usually on these, they'll tie these two to ground like they've done. So they're both running at 6 volts. So the filaments in a vacuum tube, they light the tube up so that they, you know, they have emission inside them. Modern transistors and FETs don't have filaments in them, so they don't need to glow. But that's how vacuum tubes work. So when you're looking at a tube that says 6AL5, that means that the filament voltage is around 6 volts. AL is a factory designation number, and 5 means it has 5 useful elements inside the tube. So when you see a 12AU7, you know that the filament voltage without the center tap is 12 volts around, and AU is the factory designation number, and 7 means that it has 7 useful elements inside the vacuum tube. That's how the numbering system works on vacuum tubes. Now, they get more complex as you get into the 4 digits, like 57, 51, or stuff like that. Any kind of vacuum tube, that is just more of a number. You'd have to look that up. But most of the generic tubes have that kind of a designation, a 6 or a 12, or 3 or a 1. 1V2 is like a high voltage rectifier and stuff like that, right? So again, that's what I'm going to do. I'll just go through and I'll clean all this stuff up. I'll remove this battery and see how new it is. Just let me rotate it. Just pull it out for a second here. What does it say on it? It says here March 2016. So it's probably still good. These things are very, very easy on batteries. A lot of these units still have the original batteries in them, and that's why these contacts are corroded. You can see how corroded that one contact is down there. So I'll have to clean that up. And this battery, as I say, is probably still good. I'll measure it and find out, and if not, I'll replace it. These are very easy on batteries. They're used for the ohms meter, and a lot of these you'll find still have the original mercury battery inside them, 1.35 volt battery. So that's usually a lot of the times why these are, corroded or almost rotted off at this point. But this is actually in very, very good condition. So the battery in here, I don't think really did any kind of leaking, or if it did, it was very minor. So these are all the precision resistors that make all the values correct when you read the meter. So of course, this is an analog scale, so when you're aligning this, the voltage has to align to this analog scale. There's no digital reading in here or anything like that. So the alignment is a little bit specific on a unit like this, but that shouldn't be too hard, and I'll go through that also here in the future once I get this all cleaned up. So I'll go through it and I'll get the caps in there and test everything out, and I'll come back and we'll do an alignment and maybe even look at the schematic. I'll quickly explain the bridge circuit in this vacuum tube voltmeter and how it works. This is the 12AU7 here, this vacuum tube here. These are the vacuum tubes are symbolized by these circles here. All right, and this is the bridge circuit, and this is that AC peak-to-peak rectifier here, which is that little 6AL5 tube. So again, if we were to look at the actual tubes in the schematic here, this is a 6AL5, this is the 12AU7, this is the bridge tube that we're going to be focusing on. Okay, so now, if you again wanted to look at this as a MOSFET, we would have two completely separate MOSFETs in one case here. So this would be considered the source, this would be the gate, and this would be the drain. And on this side we'd have the source, the gate, and the drain. So we'd have two completely separate MOSFETs in one glass case. Now I'm going to explain this as a vacuum tube because that's exactly what this is. And I'll start with the cathode section here. So the cathode is the part in the vacuum tube that glows orange in the center of the tube. Alright, now the cathode in this tube is indirectly heated, which means that there's a filament inside the cathode and there is no connection between the filament and the cathode. So you can picture the cathode in the vacuum tube as a pipe, and you can picture the filament running up in the center as a really hot glowing, a white hot glowing piece of wire, but you can pretend that that piece of wire has some porcelain on it, and it's causing the porcelain to glow white, and that's what's actually contacting this outer aperture here. So it's causing this to glow orange hot. Now, there is no connection between the filament and the cathode because think of being porcelain on the wire. The wire isn't actually going to touch that cathode surface, but it's going to conduct the heat through to that little metal aperture. You can kind of look at it like that. So this is known as an indirectly heated tube because, as I say, there is no heater to cathode connection. They illustrate the heaters here on this one line over here. They say 6 volts AC. And you can see here, this is the 12AU7, again with the center tap filament, because it's a 12-volt tube with a center tap, which means that you get to 6.3-volt actually filaments. These are 12.6 volts, to be precise. And this is a 6.3-volt filament, which is the 6AL5. There's no center tap because it's just a 6-volt tube here. Again, these are the filaments that go inside of the cathodes that cause them to glow orange. So now, when the cathode's glowing orange hot and there's a positive voltage on the plate of the tube, which is this upside down T, it wants to attract electrons from the cathode of this vacuum tube. So in the middle of that we have a wire grid, which kind of looks like a spring with two posts holding it centered inside the vacuum tube, okay? So now, if we have a negative voltage on the grid, it shuts this off. So what it does, it doesn't allow the electrons to pass or fly through the grid to the plate. It actually stops them from going through. When you put a positive voltage on the grid, it allows electrons to start flying through, and it causes the actual tube to conduct from the plate to the cathode. Hence, we have current draw at that particular point. So this is the bridge circuit here. We have a 10K resistor here, a 10K resistor here, a 10K resistor here, and another 10K, which is just the zero set. And that zero set is on the face of the actual meter. That's this this knob right here, the zero set. Okay. So when you zero this out, there is no difference in potential between these two plates. So what that means is they'll both sit at exactly the same voltage. If this sits at 60 volts and this sits at 60 volts, then meter is going to rest at 0 because they're both at 60 volts. There is no difference there. Okay? So what this does is this kind of acts like a scale that's perfectly balanced. If you add a little bit more weight to this side of the scale, it's going to tilt, and if you take that weight off, it comes back and centers off again. If you add weight to this side, it kind of comes down and it'll center off again. Okay, so what happens here is we can look at this line here as where the probe comes in, just simply. We'll just, ignore all the switching circuitry, and this is just, simplified. So positive voltage runs up this line into this grid here. So when you put more of a positive voltage on this grid, that causes this side to conduct more. When this conducts more, the voltage at the plate goes down. Okay, when the voltage is going down here, this is drawing more current, and there's also, this particular resistor is seeing more current, okay? So the voltage potential at the cathode of the second triode changes, and the grid of this gets biased more negatively, causing this side of the vacuum tube to shut off. So if this shuts off, the voltage at this point is going to go high. So in effect, we have this voltage going down, and now we have this voltage going up. So we have a difference in potential here, and of course now we get meter deflection on the actual meter. And that's really how simple this circuit is. There's not really much more to it. So again, you know, if you're having problems balancing out your meter or something, you obviously want to check the resistors in the bridge, because the bridge is, you know, an accurate device. If you have a really badly mismatched triode, say you have a 12AU7, that one triode's very tired and the other one's really strong, you'll find that the zero won't be able to zero it out very well. So you kind of want to get a tube with two matched sides in it, you know, as closely as you can, and then that way when you zero this thing out, it'll zero out very easily. Of course, there can be differences, and that's why you have a zero set, so that you can offset them, so that the actual, you know, you'll balance these things out. This is an external balance control, really, is what that's doing. And that's really how this circuit works. This little 6AL5 is just a peak-to-peak rectifier, and of course on the scale of the meter here, we have peak-to-peak voltages, which is in red, and RMS. And what they've done is they've just, you know, staggered the scale so that you can get your RMS and your peak-to-peak readings. Relatively simple. And that's really how this meter works, just quite simply, without going through and explaining the entire meter. So next, I'll get into the meter, as I said before, and I'll change those parts, and I'll be back and we'll do the alignment. Okay, I finished putting the capacitor in here, taking the old one out. I moved it over to here because there's no reason in having the leads run all the way up here. It's a brand new capacitor, and it's really small, so it nicely fits in here. And I cleaned off all the controls and all the contacts in there. I cleaned up the meter face just a little bit, and it has some scratching in it, but it's, you know, not too bad. It came out pretty good. One little trick, you'll notice that if you got static in the face of these meters, the meter will deflect, and it's really hard to settle it down. So if you have like a bounce dryer sheet or something like that, this is what this is here. When you take this apart, just rub the plastic with the bounce dryer sheet and do it on the inside of the meter face too. This meter is very easy to get apart. I'll show you how. Here, all you do is you just hold it and it kind of pops up. So you just hold the bottom here like that, and you just take this open like this. Now you got to be very careful with the needle. You don't want to really touch the needle. You can see there's a couple of scratches in the face there. They're not really, you have to shine the light on them the right way in order to really get them. So when this is on there, very hard to notice because of the white background. And I cleaned off all the goop under here and everything. But anyways, you can take a dryer sheet and then wipe it down really good, and then wipe down the inside also. And then of course when you put this back together, this little set here, this sets the needle 0. So you can see the needle's moving around a little bit already. And you got to make sure that this is facing straight up and down, and this is facing straight up and down when you put this on, so that there's a little knob right in here. See that little extrusion there fits right into this area in here. So again, what you do is you put the top of the meter back in first, like so, and then you very gently just put this down, and it should very gently just pop back together. And then there you go. And then you can set the 0 set on the meter right down here, and that'll bring the needle right back up to 0. So that's how these come apart, and that's a little trick in order to take the static off the face of a meter. Some of them are pretty good. You can just you know how you clean your glasses, you kind of fog them with your breath and then you wipe them off. A lot of the times that'll take the static off these too, but this one's a little bit more fussy. And I believe the reason that it is because this piece of plastic is kind of isolated from everything, that doesn't touch this whatsoever. And we have a double piece of plastic. There's another piece of plastic in here. This night symbol is kind of a plastic on plastic, so it's probably holding a charge in there. So I wiped the whole thing down, and that really helped a lot. Much better than the fogging method. So that's pretty much it. It's all ready to go. What we're going to do now is try this out. I'll in the next shot here, I'll plug this in, and of course I'll reposition the camera a little bit here so that makes it a bit easier to see. And we'll try and zero it out and see if the bridge circuit works. I did change this one tube here because it was a little bit weird. The other one was very finicky. So this is a brand new 12AU7, and the 6AL5 is okay. So as I say, in the next shot we'll fire it up. We're now ready to do a functionality check of this voltmeter before we go into any kind of an alignment. And the very first thing that you do is you set the needle to 0 with this little screw here. So there's no power applied, the thing's off. You turn this until the needle comfortably rests on the 0 mark. Now it doesn't look like it's resting on the 0 through the camera, but if you look at the meter straight on, it is right on the 0. It's just because the camera's viewing it from a bit of an angle here. So once that's done, then what you want to do is put your vacuum tube voltmeter probe on. So I have this probe here, It's an AC DC VTVM probe. It's made by Payco. They're pretty much standard. You want to check them to make sure if you have an odd probe. All it really is a switch with a 1 meg ohm resistor inside here. So when you're reading DC volts, there's a 1 meg ohm resistor in line with this, with the actual probe tip. And when it's on AC, it just bridges the resistor. And that's really all that this probe does. There's not much inside here. So I'll just screw this on here. I've tested the probe. I tested the resistance to make sure that the 1 meg ohm resistor is okay in there, and it's no problems. So that's nice and tight. So what we want to do now is turn this thing on, kind of maybe center the 0 first. About there, and we'll turn this on to positive DC volts. Usually the 1.5 volt setting is a good setting just to check the 0 out. And we'll turn this on, and we'll see if we can 0 out the bridge. That's the very first thing that we're going to check here. So let it warm up here. See if the needle settles off at all. Now what I'm going to do is I'm going to short this probe. In order to set the 0, you want this on DC, and we're going to short the probe. I've got this on positive DC volts here. So I'll just take the clip and just short the probe right out. Okay. Now what we're going to try and do is adjust the 0. And we're right at the end of the throw here to this VR. And it's not 0 setting. So that would indicate that there might be a problem in the bridge circuit. The vacuum tube is good, the 12AU7 is good, and I know that for sure. And that's one nice thing to do, is have a really good vacuum tube in there so that you're not troubleshooting the circuit and find out that it actually is the tube itself. So I know the tube is good, so the next thing that's on the list to look at is either the VR or the actual fixed resistors. And what I may do is, if I find a bunch of them that are a little bit off, what I'll do is I'll just get some really good metal film resistors and put them in. And that way I don't have to worry about the accuracy of the circuit then. It really just depends on the tube. But as you can see right now, the bridge is not balancing. That should go right down to 0. So either there's something else wrong with it, there's another open resistor somewhere, or something like that. So that'll be the next thing that we look at. We'll troubleshoot that. I'm ready to start the troubleshooting process in this vacuum tube voltmeter. The first thing you want to do is make sure that the line cord is unplugged, because we're going to be testing for ohms. We're not looking at voltage at this point. The very first thing I'm going to look at is the 0 set potentiometer and this resistor here. Now this potentiometer is 10K from end to end, and this is a 10K resistor from end to end. So we should have roughly around 5K ohms here. Now these VRs sometimes aren't exactly 10K and the resistors aren't exactly 10K. So I'm going to say comfortably between 4 and 6K ohms is what I should read from end to end, and that'll be the first test. That'll tell me that the carbon track inside this VR is making, has resistance from end to end, and this resistor is still working from end to end. So I'll do that right now. I'm using my tech meter here because the meter, the Agilient that's up here, is kind of too hard to get in the shot with this. So this tech meter is a great meter. Probably one of the nicest voltmeters I've owned, volt ohm meters. Alright, it's 4.14 k ohms. So at this point I can comfortably say that this is making continuity inside here, and this resistor is across it. So now there's a wiper inside here. Of course, when you're moving the knob either one way or the other, there's a wiper that's moving along that carbon track inside there. So if we have that wiper all the way to this end, we should have a dead short at this end and about 4K between these two. And if we do the opposite way, we should have a dead short at this end and 4K between these two. So I don't know what end this is at, or if it even is at the end, so I'll just test this quickly. I think I did put it to one end before yeah, there it is. So there's a short here, okay, and now we should read about 4K somewhere around there here, okay? You see it's climbing a bit because there's a cap that's charging somewhere. Okay, so now we know that the wiper is all the way over to this end, so technically this is shorting to this because this pin here is the wiper. So now if I move the knob all the way over to the other end, like this, I should now have a dead short between these pins, or very close. There it is, and this should read around 4K. So that's no problems there. So now I know that the carbon track in here is working. The wiper is making a connection to that carbon track, and I know that this 10K resistor is working across this. We've verified all that just by doing this one little test here. Now, in all cases, you probably won't be able to test things like that if this is, you know, tied off to ground somewhere else, or they've got this in a different kind of application. But in this application, this seems to work out just fine. If we had to, we could very easily just open 2 of these wires, and we would have our full test rate there too. But, you know, less intrusive is better. Okay? So now the next focus would be to look at the actual bridge circuit around the 12AU7 vacuum tube. And the resistors that we're going to focus on are the ones that carry a little bit of current here. And that would be this 10K resistor on the plate, this 10K resistor on the plate. We just tested this 10K and this VR here, and we know that it's okay. So R17, R19 would be 2 resistors to check. Now they're also tied into the circuit, and they've got resistors going here, there, and everywhere. So in order to accurately check these, we're going to have to open one end of these resistors. The 220 ohm resistors on the cathodes, R24 and R25, are just connecting right up to the cathodes. Now the vacuum tube is off, and you know it's not working right now. So these 220 ohm resistors look like this one end that attaches to the cathodes is just open. So it's a very high impedance at this point. So we'll be able to test these 220 ohm resistors with ease. The 12K resistor in the power supply here, this 27K resistor, and you know, some of the other ones in here, we're going to have to end up opening to test all those out. Look at this resistor up here, 91 megohms. That's pretty high up. That's this one right here. Color code says 91 megs. I don't have a resistor that's 91 megs. I'll have to open that one up and test that open. That's you know, almost you know, what would you say, reading the resistance of air between those two. That's a pretty high value resistor. So what I'll do is I'll check the 2 cathode resistors, the 220 ohm resistors right now, because as I say, it looks like it's pretty much an open circuit. So I'll poke this here and here, and that's 231 ohms. That's supposed to be 220. Alright, and we'll check this one, and that's 224 ohms. So what I'm going to do is I'm going to change these and match these as close as possible. And chances are I'll probably change out these 10K resistors also. It'll be interesting to see how far they're off. And that'll make all the, you know, the components external to the tube and the bridge circuit pretty much matched, and that should make things quite a bit better. Now here we have a 27K ohm resistor. I'll open one end of that. This is a 12K ohm resistor, and there's a 47K ohm resistor. I'll probably just end up opening all of these up and testing them. This is 3.3 megs here. This is 22 megs. I can open this up. This is a 6.8 megs up here, 22K here, and a 12K here. So since I'm in here, you know, I may as well just pretty much open one end of each one and then just go through and check all of these, so that way I don't, you know, can pretty much just eliminate everything in here. And at that point then, if there's something else wrong, I can move on from there. So when I come back, we'll test all those resistors. Alright, so what I'm going to do is unsolder one end of these resistors. Whoa, this box over here, the open voltmeter box I've got on the other side of the bench here is echoing as I'm talking. That's kind of weird. Put that face down like that. There, now I'm not hearing myself talk in that hollow box. So what I'm going to do is open one end here and just test these resistors, and I'll probably end up doing that to most of them here. So I got my Heiko gun here, and what I'll do is I'll just heat this up. And now, of course, when you're doing this, you can see they've wire wrapped these really, really tight. So grab my snippers here. So they always put an ear on here, and I don't know if you can see that in the shot here. Maybe I'll see if I can focus in, remove this. And okay, so here is the ear that they've left. I don't know if you can see that there. There's a little ear on this resistor here. And that's what they do. So what you do is you just desolder them and just clip the little ear like so. Open it, and then you've got your resistor out like that. So a lot of people will just cut the leads and, you know, kind of leave the leads hanging in the shot like so, and then they'll solder the resistor between. That's kind of hacky, and I don't like to do that at all. So when I put a new resistor in, I want it to look like it was in there from the factory, even though it's, you know, a metal film resistor. So I'll get in here and I'll heat this and desolder this one. Alright. Alright, and again there's an ear on here because they've wire wrapped this. So sometimes you don't get all the solder off, and it is a little difficult sometimes, but in most cases, you know, they do come out pretty easy. So, and that's what you do. So these two resistors are pretty much ready to test at this point. So I can get my voltmeter in here and in the shot. Maybe over here. You see it there, right at the corner of the screen. All right. So now I'll test this out. See what this reads. 10.6, not too far off. And this one is 10.46. So these are actually really close. But since I've got them desoldered, I'll probably end up changing them anyways because this is the bridge circuit, and, you know, accurate is better. So I'll end up changing these two resistors out. So what I'm going to do is I'm going to end up going through all of these and I'll end up desoldering them. I know the 220 ohm resistors are way off, and I'll check the ones in the power supply. When I get one end of them desoldered, I'll come back and we'll check these all together. It's kind of tedious to sit here and watch me desolder everything. I've now replaced all the out of tolerance resistors. You can see I've replaced the two 10K resistors here and the two 220 ohm resistors here. I replaced the resistors in the power supply area here, and at that point I said to myself, I'm so close, why not just replace the bunch that are left? It took an extra, I don't know, 5 to 10 minutes to do that. So these are really accurate values, and to give you an example, I pulled this 10K resistor out of the bin and it read 10.0K. I pulled this one out, same thing, 10.0K, and at this point I'm pretty surprised because these are carbon comp resistors. And I pulled this one out, it was 220.0 ohms. I'm like, wow, I'm on a roll, and that's where it stopped. After that, I had to pull maybe 4 220 ohm resistors like this out to get a 220.0 ohm resistor for this one. So I did grade all of these resistors. They're all right on exactly what they are. This is a 22 meg resistor, and it's what it says it is. This is a 6.8 meg resistor. I replaced this, if you recall, it was about 7 point something megs. So I replaced that. You'll also notice that I replaced both these caps. Now, I didn't replace them for any electrical reason. It's just that the person that assembled this wound the legs of that ceramic cap so tight on the original 6.8 meg resistor that I'd have to probably cut it off and I'd have no leads left, or just by unwinding them I'd probably destroy the cap. So I just replaced these two caps. This goes from one grid to ground, this cap here, and this goes from the other grid to ground. So they're just two matching valued capacitors there. As I said earlier, these ceramic caps very, very rarely fail. So you know, these are you know, almost the most resilient component in here, I would think. Whereas its wax capacitor counterpart is the exact opposite of these. If you have any wax caps in here, they all have to go. So what else can I tell you here? I replaced the 10K resistor down here on the zeroing potentiometer down here. These resistors on this switch here, you don't want to replace any of them. They're very, very high accuracy resistors, and this will affect the actual scale accuracy. So unless you have to replace any of these resistors, do not replace them. And if you do, you're going to be twisting a bunch of resistors together to make the exact value. To give you an example of some of these values, one of them is 138 k ohms. Another one is 315 k ohms. So they're like that. As I say, test them all, and as long as they're very close to their value, you want to just leave these alone. So these are all good, and as I say, I've pretty much changed out all the resistors in the bridge circuit and in the calibration area, and that should make this a very accurate circuit. Now, I'm going to hold on to this for a while, unless of course somebody twists my rubber arm and, you know, talks me out of this thing, or, you know, trades me for something else. But this is going to be very nice for looking at, you know, AVC voltage and you know, aligning the RF section in receivers and stuff like that. And that's kind of one of the reasons why I'm going to do this, or why I've actually gone through this vacuum tube voltmeter. What else can I tell you about this? These values originally, I think this one was 231 ohms, the one that I removed, and this one was 224, I think we measured, if I remember correctly. That isn't all that incredibly far off, and these 10k ohm resistors weren't all that incredibly far out, and I have a feeling that this potentiometer should have probably balanced the bridge. So we might have another problem here that I haven't come across yet. But what I'm going to do is I'm going to turn this around, I'm going to fire it up, and we'll see if we can zero it out. And if it zeros, we're on to the next step. We'll go and do the alignment on all the scales. And if not, I'll turn it back around and we'll start going through another troubleshooting procedure until we actually find the troubled component. So that'll be the next step. We're now at the point to where we're going to try this out and see if we can make this thing zero. So the first thing that I'm going to do is I'm going to put the zero right in the center. So that's that little dot right down. You can see it kind of goes to here, it goes to here, so that's roughly the center. And I'm going to leave this on the 1.5 volt scale, and I'll turn this to positive DC volts. Now, we shouldn't need a probe on this. We're just trying to course zero it. We're not looking for any kind of accuracy. When we're doing an alignment, we'll have to have a probe, and we'll have to ground that probe out at that time. But for this setting, I'm not really too worried about it. It should zero relatively easy like this. So I have to plug the unit in. I cleaned the plug up here. I put it in the sandblaster very quickly, and I just buzzed these sides here. They were actually very corroded. It would be very hard to sand this off, because I don't know, the thing was in a bucket of water or something like that. It was very corroded, but at any rate, it turned out very nice. You can see it looks like a brand new plug pretty much, and the cord's very nice on it, so I figure I'll just end up using this cord. So I give it a light sanding with some sandpaper in the end too, just to give it a bit of a smooth texture, because after you sandblast it, it does leave a little bit of a coarse surface on there. So I'll plug this in here, and we'll turn it on to positive DC volts. Now you can see that the meter is pegging out here. We have to wait for the vacuum tube to warm up, which takes roughly about 15 seconds. In the data books they say about 11 seconds, but in more reality I'd say about 15 seconds or so before emission really starts to really take place. So, doesn't look like we have any zero. I figure it would come back a little bit. It's in the center, so I'll turn it here. No, nothing there. Well, it's coming down a little bit at this end, but that's not correct. It should, when I move this, it should very quickly zero, and it's not doing that at all. So there is still a problem in the zeroing circuit, or in the actual bridge circuit. So we know already that we have a new tube, we've replaced all the resistors, so we can pretty much discount all of that stuff. The meter itself works good. When I turn it off, you can see it very comfortably rests at zero. There's nothing wrong with the movement. It moves fluidly up and down. So you can pretty much say that the meter is good. So it's going to be some other component inside here that's either gone haywire, or there is something wrong. So what I'll do next is I'll turn this back around again, and with voltage on this, we'll look for the problem electrically, and that should bring us to the issue very, very quickly. Okay, let's troubleshoot this thing and find out why we can't seem to get that bridge to balance. So the very first thing that I'm going to do here is put power to this circuit. I got to let it warm up, and we're going to start troubleshooting the actual bridge circuit while it's live. Now, in order to do this kind of troubleshooting, you need to know what you're doing. You need to understand that vacuum tube equipment has high voltage in there, so if you're unfamiliar with this kind of stuff, you don't want to troubleshoot anything like this. If you're going to work on any kind of high voltage equipment, or any equipment at all, you're doing so at your own risk. So unless you know and you're familiar with vacuum tube equipment, I highly suggest you learn about it before you go and troubleshoot anything that's live. There's really high voltages in here, and you can really get hurt if you touch the wrong thing. So what I'll do is I'll plug this in, and I'll let it warm up. So a little neon bulb is on up here. I don't know if you can see that. So it's warming up right now. Now I've centered the control. I've centered the actual zeroing control in the middle here, and what we're going to do is we're going to start testing some voltages in the bridge circuit and find out why it isn't actually balancing. So in order for that needle to sit at zero, the two plates of this 12AU7 need to be at exactly the same voltage. And if they're different, then we know that we're not going to actually have any kind of a needle zero there. So when we look at the schematic here, we can see that we have the two plates here on the tube. This is pin 1 and pin 6 are the plates, pin 8 and pin 3 are the cathodes, and pin 2 and pin 7 are the grids. So what I'm going to do first is I'm going to just center this 0, the actual VR on the front, the actual zeroing VR. And at the top end of these 10K resistors, which is R17 and R19, I'm going to just equalize the voltage so the voltages are somewhat the same and see if we can actually equalize them at this point. So I can test them at these two resistors here. These are the two ends of the 10K resistors that go up to the plate. So these two sides of these resistors are what run down to this VR. Now I've got the negative of my voltmeter just clipped to the chassis of this, and this is the positive probe, and I'm reading DC volts here. Now they've got a bunch of voltages here, first of all, that are rated. This is 60 volts and 60 volts on the plates, and you know, a whole bunch of voltages. And this has been taken with a 20 ohms, k ohms per voltmeter. Now, you know, that's a relatively low resistance meter. These are much higher resistance, so we can expect higher readings on this digital voltmeter. So I guess they're figuring when they sell you a vacuum tube voltmeter, your actual test gear is probably not a vacuum tube voltmeter. So you probably have an old meter with a 20 k ohm per volt sensitivity. So that's why they've used that kind of meter, so that you can troubleshoot this if there's something wrong with it. So this, of course, is, you know, way back in the day, right? So what I'm going to do is I'm going to put my resistor, my probe on this resistor here. This is going to the VR. We have 45 volts here, and we have 47 here. So now what I'm going to do is I'm going to turn that VR from the other side, and I'm just going to match the voltages. You can see if I turn the VR here, it'll be 45, and I take 46, and 47. So I'll turn it to about 46.2 here, and we'll go over to this one and see what it is, 46.5. So we're getting pretty close. So I'll just turn this a little bit this way here, right about there. No, a little too far. It's going to be a little bit unstable because my soldering irons are turning on and off and on and off and on and off, and they're both turning on and off at different times, and it's, you know, pulling the voltage up and down at my bench here, so it'll be just a little bit unstable. This doesn't have a regulated supply in it. So 46.1, something like that. This is 46.321. So that's close enough. So we're pretty good. Okay, right about there. So close enough. So we're at 46 volts on each side here. So now let's look at the cathodes. These are the two cathodes that come off of each of these, the two triodes in this 12AU7 here. So let's hold this here. Here. So I got about 26.2 volts on that cathode, and 26.2 volts on that cathode too, so they're relatively well balanced at that point. So now let's look at the grid voltage on these two triodes here. So this is one grid here, which have a negative voltage, yeah, 24.8 there, and we'll look at the other grid, which is right here, 24.8. So it's relatively well balanced with that you know, potentiometer right in the center. Now let's look at the plates. Now these plates obviously are going to have a different potential because it's not sitting at 0. So let's look at the differences here. Wow, that's pretty low. 7 volts on the plate. Okay. And here we have 17.9 volts on the plate. So that difference between 7 and 17 volts is what's causing the needle to deflect on the meter. Okay. So that's really low. So now, if we look at this one here, we see that there's 17.9 volts on here, and we see that there's one pink wire or red wire that runs off into this gray sheathing right here. All right, this gray sheathing comes out over here, and this red wire is right here. This is the same red wire, and it runs up to this wafer switch inside here, and that's not going anywhere. It's not connected to anything right now. So it should be the same voltage, 17.9 and 17.9. So yeah, that's the wire, and it's not going anywhere. So there really is no load on this side. Now when we go to this side here, we see that this is at 7.7 volts. And that's very low. It's supposed to be upwards around 60 volts, it says on there. It's probably going to be more like 70 or something because this is a much higher impedance meter, right? So it's about 7.6 volts here, and this runs off through this yellow wire here over to this VR over here. Now that kind of makes me raise my eyebrow because you know, this is extremely low voltage on this plate here, so something's dragging this off. So we go over here, if we want to follow this through this VR, it goes out to this gray line here. This gray line runs into this white kind of a sheath, this wire, and that comes out over here. And that gray wire looks to be the same color here. Yeah, that's about the same color. So I'll look at this end here, and that's also not connected to anything right now. So this is just open. So we'll test this here. This is 280 millivolts here, and you know, well, it's moving around a little. That's moving around all over the place as I touch that. Okay, so this is already kind of looking suspect to me. Alright. So again, we have about 7.6 volts here and 17 volts here. So this is much lower. So if there's something dragging it down, I would think that it's probably in this line here somewhere. So what I'll do is I'll hold this and very carefully move this. Okay, so this is where this is running into. Right, we have our 7.7 volts right here, as you can see on the screen there. Okay. Alright, so now this end of the VR is open, so we should have roughly the same voltage there because there's nothing loading this side down, right? Yep, 7.4 or close to, right? Now this gray line here is open. We see it running up to this switch here, and there's nothing connected to it at the switch. That little finger is open in the switch, and it should read roughly the same. And we only have about, well, it's fluctuating in the millivolts here, so this is under 1 volt here. And here again we have 7 volts. So there should be no reason why this is down so low. This is a 10K potentiometer here, okay? So if this was sitting, if the wiper was sitting right in the middle, there'd be 5K to this end and 5K to this end. Alright, so as you can see here, this end's open and we have the same voltage, right? Because there's nothing loading it down really. There shouldn't be really, you know, much of a difference whatsoever in the voltage. And this wire here is open too. And we can see that the voltage is much lower at this point. So right now, right off the bat, it's leading me to think that this VR has some internal form of leakage to ground. So what I'm going to do is unplug the unit here. Unplugged it, the voltage is off, and nothing here anymore. There's hardly any capacitance in this circuit. The voltage drains off really quickly. So since this isn't connected anywhere in the circuit, this is just floating right now. This is the 0.5 volts DC calibration, and we're on the 1.5 volt scale, as you remember from before. So this isn't even hooked up into circuit. That's why it's open on this finger in this switch over here. So what I can do is I can just lift these wires out of the VR. I put these new resistors in here, so the wires have been freshly clipped. So this will all come out really easy. As I say, I don't bend them. There's no point to, and this is the exact reason right here. So I'll heat that up, and these just come out just that easy. And I'll take this wire out too. Okay. So now what I'm doing is I'm isolating this area from this VR because this looks like the leakage to ground. Alright, so what I'll do is I'll just tack these together, and I'll put this little yellow wire here like so, and add a bit of solder to that, and we'll be able to test this very easily to see if there is leakage in that VR. If we have any change in the circuit here, we'll know definitely that this is somewhat maybe leaking to ground inside or something like that. Again, this isn't in circuit. There's really no connection to anything. This is just tied to this post, and this is open and this is open. So we can just float these two resistors and this wire, and it should be absolutely no difference if this VR is fine. And if there is a leakage, we should get a dramatic difference here. So what I'm going to do now is plug this back in. Alright. I will just let this warm up for a second here again, because we have to wait for that vacuum tube's emission to start. And then what I'll do is I'll go back to the plates here again, and I'll test the voltage on the plates and see what kind of voltage we get and if that's changed anything. Okay, we should be close to getting emission now. So, here's one. Look at that, 68 volts. And we'll go over here. 70 volts. So that's more around where we're supposed to be. So I can pretty comfortably say that this VR is leaking. So now what I'll do is I'll move this over and we'll probably be able to zero this thing out. So I'll very carefully move this. Okay, so I'll just try and zero this. As I say, we probably don't need this on here right now because we're just going to course zero this. And of course, there we go. We can zero it, no problems. So when this sits at the 0 line right here, because it's sitting at the 0, technically it's balanced. So the voltage on those two plates right now should be very close to each other. So this is working, so that definitely is a problem. We're going to have to take that VR out, and I'll open it up and we'll take a look at it under the microscope and see if we can find some sort of a carbon trail inside of it, or some sort of a short or something like that. But I'll just show you that the bridge is in balance now. Hopefully when I move this it doesn't turn that knob, but it'll give you an idea of how close the voltages will be. So I got my voltmeter here again, put this to the chassis. Okay, so I'll test the plate here, and we see that we got 71.5, maybe 6 volts here, very close to, okay. And I'll touch this one, and 71.5.6 volts, you can see there again. So that's telling you that now the bridge is actually balanced, and the voltages are the same so that the actual needle can rest down at 0. So that looks like the problem. So what I'm going to do next here is I will remove this VR out of here. I still have to desolder that gray wire off of it and stuff, and get it out of the chassis, and then we'll take it apart and look at it under the microscope and see if we can find what's wrong with it. I now have the VR removed from the vacuum tube voltmeter, and this was mounted up against the chassis like this, and then of course this is the side that we adjust, and you can access this through the actual side of the case of the vacuum tube voltmeter, so you can adjust it even when it's put back together. So this side here, the opposite side, is up against the chassis, and this is the side we need to get to in order to remove the cover on this. You can see there's a couple of tangs that have been folded over here that hold the case on, and they're very easy to get open with just a pair of sharp clippers. And what you do is you just grab it like so and then kind of bend them upwards. So you got one there bent up, and I'll bend this one up over here, get it from this side, like so, and then like so, and then I'll come over here and grab this one like so. Alright, and there's quite a bit of spring tension in here. This whole thing really just comes right apart. So you can see inside here, this is how this is put together. This is the carbon track right here that the wiper runs along, and this here is the wiper. And then of course it makes contact to this little center rail here, and then as you can see, this little piece right up here, I don't know if you can see that right up in there, that rubs along the wiper. So that's what gives us our variable resistance inside of this VR. Now, there is some form of leakage or a short or something like that to ground in here, and I don't know where that leakage is at this point, but what I'm going to do is I'm going to spend some time and try and find where that low ohms leakage is, and I'll be back, and we'll come back at that particular point. Now, I'm not too sure if you can see this in here, but there's a couple of just hair-thin little steel wires that looks like steel wool in here. And there's a little one that runs from here, and it looks like it's connecting to the cap. The cap is really close tolerance to this carbon track here as it goes around, as it cups in it. There's a little piece of that steel wire right here. So there's looks like there's some form of steel wool or something in here. Maybe somebody had cleaned this thing up at one time and had got some steel wool or something in here. So what I'm going to do is I'm just going to clean this up really well and brush it out, and that should probably fix the problem. It doesn't look like there's actually any arcing or any kind of trails through here or anything like that to the case. The case just is in very close tolerance around here. Of course, this cup right here, you can kind of see it in the shot. I'll have to push this out of the way. This just kind of goes on top, and then that fits inside this like so. So I'll put this together like this. Keep a close eye on my camera here. I got the zoomed right in. You can see how that fits there, right? So now if that little piece of steel wool is joining from here to the case, or very, very close to, and it was on the other side. There's a really long piece on the other side. I've lost it. I don't know where it is, but it's under my microscope. You can just see it. Just hair thin wires, and you can just brush them off. So you can see what kind of a close tolerance that is to this actual carbon track here. I have a piece of that little steel wire right now, right on the tip of this. So that's what's going on here. So I'll just clean this out and put it back together, and I think this will probably be okay. We'll give it a shot and try it out again. Alright, I've got the VR put back in. I haven't tightened the little tangs on the other side. There's these two little tangs that you twist to lock this thing in here, and I haven't tightened those up because just in case there is an issue I can remove this relatively easy. You can see how loose that is. So I've soldered the wires back onto it, and of course it's enough to make a ground connection to the actual chassis here if there is something wrong. You can see on this side here, you look in here, you can see how these little tangs lock the VRs in. So you give them a bit of a twist and it locks them in. You can see this one here if I wiggle it. See, it's still loose in there, and they're pretty much straight still. So when I want to lock it in, I'll just give them a twist with a plier, and then this little VR will get locked in. So I'm pretty much ready to try this thing out. I'll put the little 6AL5 tube back in here. It's a cute little tube. Alright. And I'll plug it in. And we'll see what happens. Hopefully this works. It's on right now. Everything's been switched on. It's still on from before. And it's starting to look like it's emission starting up. Here we go. It's looking good, so looks like I can zero it out. No problems with the zeroing. I'll wiggle this around a little. Looks good. No problems with the zero. So that definitely was the problem. So what I'll do is I'll get this put back together, and at that point I have a feeling we're going to be ready to do an alignment. Just an interesting little side note here. This is a brand new 12AU7 out of a box that I've got, and I was going to use this as the replacement for the 12AU7 that was in here. Now you'll notice right away that when I move this around here, you'll see how when I zero that out, this is pointing at about 3 o'clock or just around 3 o'clock, and it's moving around a little bit. So this triode here, move that right to about there, at about 3 o'clock it kind of settles off once it's warmed up. What this is telling me is that the two triodes inside of this 12AU7 are very mismatched. So we have all precision components now in this circuit. We have matched 10K resistors, and we have matched 220 ohm resistors, and all that kind of stuff. And of course we even have a matched very high precision 10K resistor across this VR here. So now when I move this to the center to 6 o'clock, this is where the voltage will be equal to each plate of this 12AU7. So technically this should rest right at 0 at this point if it has two very well matched triodes inside. So you can see this is 6 o'clock here. If I move it to here, this is one extreme here, and this is the other extreme here. So 6 o'clock is the center. So I've taken the time to match up the triodes inside of one 12AU7, and I'll do a video on that sometime. It's a little adapter I made for my oscilloscope in a small circuit. So I'll pull this 12AU7 out of here, and I'll put the well-matched one inside. I'll put this back to about 3 o'clock here, where this other tube sits. And we have to wait for this to warm up. In order for this to be a real fair representation, this should actually warm up for about 5 minutes or so, but you'll get the gist of how this works. So you can see that, the needle is kind of pegged the opposite way right now because this is at 3 o'clock. So I'll advance this to around 6 o'clock. You can see that's just about at 6 o'clock. It's a little bit before, and as the tube warms up, it'll move a bit, and this will come right into 6 o'clock. Now the two triodes inside that 12AU7 are very, very well matched, and I'm going to leave that 12AU7 in this night vacuum tube voltmeter just because I spent the time to match them up. So you can see it's moving just a little bit here. As it warms up, that will settle down and it will stay right on the 0 mark there. So give about 5 minutes or so or something like that, and it'll, you know, completely be stable there. So this is a really good representation with the circuit of how you can get a 12AU7 and both the triodes inside are quite different from each other. And this goes for brand new tubes. This is brand new old stock here, and you can also, you know, brand new 12AU7s right from the store will probably also have this to some inherent degree unless they have been matched on a special machine. And most of the companies don't actually spend the time to match each vacuum tube. So that gives you an idea of how mismatched a brand new tube can actually be. So there you go, just one interesting little side note. I guess one could modify one of these things to match vacuum tubes. Maybe one day I'll do a video on that too. One additional note, if you own this Knight KG625 vacuum tube voltmeter and you're following along, before you put this back into the case and we go through the alignment procedure together, you want to check one thing. Now, the R times 1 setting is the low ohm setting, and I had a little bit of problems with that actual setting and zeroing this meter out. So you will probably want to check the ground on this barrel first, and I'll explain how you go about doing this. So first of all, if you have your voltmeter pretty much done, of course none of these VRs on the side here are aligned at this point, but when you shut the meter off, when you actually shut this off, as long as this is zeroed, so you've adjusted this little plastic set screw here, so when there's no power applied, the needle rests on the 0. That's the very first thing you need to do. And then after that, you, of course, turn it on, let it warm up a little bit, and then you go to positive DC volts, alright, and in order to align the ohm meter here, you just need these two controls and a fresh battery inside. That's all you need. You don't need to align anything on the side here. So go to positive DC volts, put this into the 0.5 volt DC setting. With your probe on, short the probe to this clip here with it with the probe switched to DC, and then zero this out to the 0 line. And then of course unclip this from your probe, put it back into the AC ohm setting, click this to ohms, and put this onto R times 1 ohms. Alright, now what's going to happen is if your probe is open, this needle should deflect somewhere. So this setting here aligns the top end of the scale. So you see that little infinity symbol there, that little sideways 8? That's what you align here. So what you do is you take this knob and you just align that to the infinitive setting at this point, and you don't touch the 0 or anything because you just aligned that. So now the scale should be aligned. Now when you short your vacuum tube voltmeter probe to this clip here, alright, this should go right down to 0. Now I found that mine only went down to 1.5 ohms in the beginning. And I checked all the resistors on this, again, this one switch here behind, and everything's fine, because I checked them before. I just double checked because I'm thinking I must have missed something. But what the problem was is it turned out to be the ground connection on this barrel. So this barrel is tightened to the back of this aluminum panel, and then this aluminum panel is screwed to this metal chassis here, and it presents some resistance between the metal chassis to this jack here. Now I tightened this up and I tightened the metal chassis up, and still, it moved around just a little bit, but there was still just a little bit of resistance there. So now that I've done this, you can see I don't have my probe hooked up, but I can kind of cheat by just doing this here. You'll see it'll go right down to the 0 mark now. See, it's right on the 0 there. And that's what it's supposed to do. So with no connection, it should sit at the 8. And then, of course, when you short your probe, of course, your probe is screwed on here, and you have it in the AC ohm setting. When you short the two, it should go right down to 0. Now, if you have a very long wire coming off of your probe, this will probably reflect maybe a little bit of that resistance. It may or may not, just depending on how you've zeroed this out. So now I'm going to show you what I did in order to fix this problem. So what I did here, this wire I bridged to this chassis here. So this is a metal chassis, and it has a plating on it, and that's screwed to this aluminum face, and it's basically held on by these screws, so that's in the back side of the meter. So this is tightened onto this aluminum panel here, and then this aluminum panel runs over to here, and then we have a metal jack with a star washer under it, and they've tightened that jack onto this star washer really tight, and there's a soft kind of a Bakelite washer, or I should say a fiber washer on the other side, so that when you tighten the barrel down, it doesn't bottom out on the face of the actual voltmeter. So I tightened this as tight as I basically could without causing any issues, and then I checked the ground here. Everything seems to be okay, but there was still some resistance. So what I did is I took my voltmeter probe and I touched it right to this metal chassis, and of course it went right down to 0, so that I know that there's obviously some resistance between this chassis, this metal, the aluminum face, and this jack. So what I did is I soldered a piece of number 10 wire, a really thick wire, right down to the actual jack. And then of course this wire with the knot is this ground probe here. So that will probably solve your low ohms issues. That'll be one of them if you do have this meter and you can't get it to 0 out. So you're going to have a pretty hot soldering iron to solder to this chassis. This looks like about 18 or 16 gauge bent steel here, and then of course they have, it looks like it's got a coating on it. It solders really easy with a nice hot iron, and of course what I use is my Weller 250 watt iron here. And I have a piece of number 10 wire just bridged into the tip here, and of course it runs in and then it angles out these. And I'll get into this in probably another video, but if you want to solder any really thick chassis, having the normal Weller tip, it usually comes out to about here, just won't do it. So when I click this is hot right now, and you can solder the chassis, and I've been doing this for years and years and years, and it works absolutely awesome. The only one downfall to having this here is that the number 10 wire will go away really quick here. So, if you're using this on a relatively constant basis, you're going to be changing this every now and then. If I was going to use this for, say, a week continuous, it would probably go through one piece of number 10 wire. But as long as you have scrap pieces of number 10 solid wire around, you have no problems. You just bend up a new tip, tighten it in, and away you go. So once you start using this is the best thing since sliced bread, let me tell you. Solder to any size large chassis you want, any big radio chassis, you'll get a nice puddle on the chassis by using this particular method. I'll get into that in another video. So anyways, you're going to need a really hot iron to solder this to here, and then of course down to here to this jack. There's a tab that comes off the back side of this barrel that doesn't really require all that much heat, so you can probably get away with your normal iron just soldering that to here. And you'll have a very good ground connection at this point, and you should be able to zero out your ohms meter. So again, I'm going to put this into the case, and I don't want to take this out again, so I just did that ohms check before I did that. I checked all that scale, because when we get into this alignment here, I plan on leaving it in the case. Now, the actual factory alignment procedure for this voltmeter here, when you're aligning these VRs on the side here, requires you to take this out of the case. And I'm going to show you how to get around that, so you don't have to remove this from the case once it's warm and then tie into this and then put it back in the case again and put all the screws back in. That's a real pain to do it that way. So with some of the modern test gear we have, and some power supplies and stuff like that, we can get right around all that, put this in the case one time and get that over with. And I'm pretty sure that some of the other voltmeters that are designed this same way, they want you to do the same thing, so you can probably use this test setup or test fixture that we're going to put together for your next vacuum tube voltmeter if you're going to do another one. We're now ready to perform the calibration procedure on this Knight vacuum tube voltmeter. It's all put back together and it's been warming up for about 2 hours, and that's about the time they want you to warm this up for before you do perform a calibration procedure. So in order to do this, you need a plastic screwdriver with a plastic tip on it, and we'll have to access the potentiometers behind these holes in the side of this vacuum tube voltmeter. So in order to do that, you'll need to remove the bracket that supports this VTVM. So they're very clearly marked on the side of the VTVM, 1.5 volt DC cal and so on, so it makes that pretty easy to find as we're going through and doing the procedure. Now again, this procedure does involve the use of some high voltage, so if you're unfamiliar with high voltage, do not do this procedure and do not do the calibration. Remember, if you're following along, you're doing so at your own risk. So next, we're going to take a look at the actual data sheet and follow their calibration procedure. We're now ready to perform the alignment procedure on this VTVM. So this calibration paper is available online, and in fact the entire datasheet booklet on this VTVM is available online. They're very easy to find. This is a pretty common vacuum tube voltmeter. So I'm going to narrate this maintenance procedure and calibration procedure a little bit because we now have modern test gear available to us, and that'll make our alignment procedure quite a bit easier. And I'll explain that as I go. So it says here, the calibration controls are located at the left side of your VTVM and are accessible through the holes provided at the side of the cabinet. Now those are those holes that we just looked at in the side of the vacuum tube voltmeter. The instrument must be removed from the swivel stand to permit you to use these holes. Now that swivel stand looks like this, and it bolts to the side of the meter through here, and of course this blocks those calibration holes, so you need to remove this stand just for that reason. It says here you should recheck the calibration of the instrument if you find it necessary to replace any parts, especially if you replace a tube. Well, we've pretty much completely rebuilt this entire vacuum tube voltmeter, so a calibration is definitely needed. It says here, keep in mind that the accuracy of your VTVM depends on the accuracy of the standard used. Thus, if the greatest accuracy is desired, use an external standard of known accuracy for calibration. So what we're going to do is we're going to use a power supply, and I've created a voltage dividing network, and I'll explain that here as I go, so we don't even need to look at this next part right here. It says here, check the mechanical zero adjustment of the meter before you make any calibration adjustments. So now that's this little plastic set screw here, and this needs to be adjusted with this meter in the off position and it unplugged from the wall completely. So before you do this, you want to make sure that there's no static charge on the face of this meter. And what I do is I use a bounce dryer sheet, and I just rub the face of the meter with this bounce dryer sheet. And of course, then I touch the meter and it'll discharge any static charge on here. So this is a really bad offender for holding a static charge. If you rub this with your hand, the needle will go like this and stay up like this, and it'll stay there for a long time. And I think that's due to this plastic meter face, and of course this night symbol is another piece of plastic, so I think it's acting as a form of capacitor here and holding a charge between these two plastics. So before I put the meter face together, I actually wiped down the inside of the meter with that bounce sheet too, and that really helped to keep the needle settle down at the bottom here. So this will stay like, you know, the needle will stay like this for, it seems, forever if you don't discharge the face. So that's very important before you set this, because if you set this and this has a charge on it, this will be fighting the charge that's pulling the actual needle up. So you'll need to make sure that this meter face is completely neutral. Again, the meter has to be completely unplugged. This has to be in the off position, because when this is in the off position, it actually shorts the movement in the back of the meter to ground. So of course, when you're transporting this, you always want this in the off position. So you have to do that first, all right? It says here, disconnect the VTVM line cord from the AC power outlet. That's what we just discussed, with a non-metallic screwdriver such as this plastic one right here. Adjust the plastic screw in the lower center of the meter face to bring the meter needle to exactly 0 at the left side of the scale. So that's what we just talked about here. Plug the line cord into an AC power outlet and allow the VTVM to warm up for 2 hours before proceeding. Now that's what I've done already. I've already warmed this up for a couple of hours here. It says here, caution, do not use the VTVM on a grounded metal bench radiator or other grounded object. During part of the calibration procedure, the instrument will be out of the case. Now, we're not going to do that. We're not going to remove this from the case. We're going to do all of the alignment procedure with this inside the case. And we can do that now because of modern test gear and, of course, our external voltage standard here. And I'll show you how to set that all up. It says here the 120 volt power line voltage and internal voltages will be exposed at this time. Never touch any of the exposed wiring while the instrument is plugged in. Again, we're not doing this procedure, but a good thing to always note, always be careful when you have this thing exposed. So next we're going to go through and actually do the 0 adjustment, and we'll work our way down the calibration sheet. We're now ready to do the 0 adjustment procedure. So it says here, set the function switch to positive DC volts. So this is the function switch, and it is on positive DC volts. That would be ohms. That's positive DC volts here. Next it says set the range switch to 0.5 volts DC. So this is the 0.5 volt DC position. So I have to turn it down there. It says here, connect the probe lead to the VTVM and connect the common lead to the probe tip. So we've already got the probe connected to the VTVM. Okay, so now what they want us to do is short the tip of the probe out right here. So we're going to take the common and just short the tip of the probe out, okay? It says next here, set the probe switch to DC. Okay, so that's the switch on the actual probe. This is AC in ohms, and that's DC. You want to make sure it's in DC. When this is in DC, there's a 1 mega ohm resistor in line with the center conductor of this. When you have it in AC ohms, it shorts the 1 meg ohm resistor, and this tip of the probe just runs directly into the line that runs to the VTVM. So it needs to be in the DC position. Okay? It says here, adjust the zero control to bring the meter needle exactly to zero at the left side of the scale. Okay, so now what we need to do is adjust this zero control and bring this needle right to the zero. Okay, right there is zero to my eye. Might look a little bit different in the camera, but straight on, that's zero. It says remove the connection between the probe tip and the common lead. So basically it's just telling us to open the short. That's all it's doing. It says here, note the meter needle will jump when the probe connection is removed from the common lead. This is normal when set in the 0.5 volt DC position. And it did move just a little bit, not a big deal. So when I come back, we'll do the DC voltage calibration. That is the next step. We're now ready to perform the DC voltage calibration in this vacuum tube voltmeter. The calibration of all DC voltage scales above 0.5 volts is accomplished with the 1.5 volt DC cal control. So that's the calibration control right at the top. That's the top hole in the side of the case. As we noted earlier in the video, we looked at those 4 holes in the side of the case. Those are the calibration points. It says set the function switch to positive DC volts. This is on positive DC volts right now. Set the range switch to 1.5 volts. That's 1.5 volts right here. Set the probe switch to DC. That's the switch on the probe. It is to DC still from the earlier procedure. Recheck zero adjustment with the input leads connected together. So what they want us to do is make sure that the meter is still zeroed. So we're going to short the probe again, like this. And I will reset the zero. It is right on the zero right now, so I don't even need to touch this control. It says remove the battery from the VTVM and connect the probe tip to the positive end of the battery and connect the common lead to the negative end of the battery. So what they want us to do here is remove this from the case again and remove that 1.5 volt DC battery in there that's used for the ohms and use that as the standard in order to align this scale. Well, we're not going to do that because I have an external 1.5 volt source. Now what I have is a variable power supply that I've set to 2 volts. And I have 4 10 ohm resistors in series to ground. So right at the beginning I have 2 volts, I have 1.5 volts here, 1 volt here, 0.5 volts here, and then of course we're at ground. So we're going to need 1.5 volts for one of the calibration procedures, and we're going to need 0.5 volts for another calibration procedure. And we're going to also need a 5 volt source, which is also comes out of that same power supply. So you could actually put that little schematic together if you needed to get 2 volts down to all the voltages that you need. So that's this particular section here that we're going to ignore. So it says then, adjust the 1.5 volt DC calibration control through the hole in the side of the cabinet so the meter needle rests exactly at the red dot to the right end of this 1.5 DC scale. Now, you notice that we have 1.5 volts DC here, but we have that little red dot here. Now, why would they want us to align a 1.5 volt source to a red dot when the 1.5 volts is there? Reason being, the battery, the C-cell that's inside here, and all brand new alkaline batteries are about 1.6 and a bit volts. They're usually never at 1.5 right on. So by aligning it to that red dot is bringing it into the 1.6 volt area. So since we have a 1.5 volt standard, I can now align this right to that 1.5 volt line. You'll see the voltmeter here. That's kind of peeking around back of this. I'll test the that first resistor after the 2 volts. And I'll show you, if you watch the voltmeter there, that's what we're at, 1.5 volts right on. Now that's way more accurate than we actually need to be. If it was 1.502, it would be okay. But this is 1.500. And now I need to connect the actual probe here. I'll remove the short and I'll connect the ground to the negative of that 1.5 volt source, and then this to the positive of the 1.5 volt source. And I'll do that right now. Okay, so now you can see that we're off the scale here, so I need to poke my insulated screwdriver through the side of the case here and adjust that. So I need to adjust that right down to 1.5 volts. And that's 1.5 volts right on. So now it says here, reinstall the battery in the VTVM. It says here, if a mercury cell is available, you may calibrate the DC voltage ranges by setting the needle to 1.35 volts, because that's where a mercury cell sits, and it's a very accurate voltage source to do this, but you don't need to do this, and of course these are really unavailable now, so the 1.5 volt voltage source and that division network with all those resistors there is usually the way to go. So that really completes that part of the calibration. So after this, we're now going to be on to the 0.5 volt DC calibration, and that's the next one in the list. We're now going to perform the 0.5 volt DC calibration procedure for this vacuum tube voltmeter. It says here the VTVM must be taken out of the cabinet for this adjustment. Now again, we're not going to remove this from the cabinet. We're going to use this voltage division network, and we're just going to tap off at the 0.5 volt mark here. It says here, set the function switch to positive DC volts. Got it at positive DC volts here. It says set the range switch to 1.5 volts. This is 1.5 volts right here, so it's set there. It says the accuracy of the 0.5 volt calibration depends on the calibration of the 1.5 volt range. Therefore, 0.5 volt calibration should be done only after the 1.5 volt DC calibration has been set. So we've already done that. We have nothing to worry about. It says set the probe switch to DC. So we still have it at DC from before. It says here, recheck the zero adjustment with the input leads connected together. Be sure to perform this step before going on. So they want us just to make sure that the meter is zeroed again. So we just short the two again, and we check the zeroing, and we're pretty much right on. So straight on, this looks like it's right on the zero mark. Through the camera, it might be off just a little bit. It's just right on the verge. I could probably just move that a hair, right about there. That would be absolutely straight up and down. A little bit too finicky probably to be doing this adjustment, but that's right on the zero right now. Okay, it says here, connect the probe tip to the center terminal of R21, the AC0 control, and adjust this control to exactly 0.5 volts on the 1.5 volt DC meter scale. Now we don't need to do this step whatsoever. So it says here, leave the probe connected to the center terminal of R21 and reset the range switch to 0.5 volts DC. Now carefully adjust the 0.5 volt DC calibration R29 so the meter needle indicates exactly 5.0 on the meter scale. Meter reading is now 0.5 volts. So we can skip all of this, and what we can do is attach this to our 0.5 volt source and just align this R29, which is in the side of the cabinet. That's the second setting down on the side of the cabinet here. So if we look, we have the 1.5 volt cal here, and then we have the 0.5 volt DC cal here. And what they're wanting us to do is set this so the needle sits right at the 5.0 right here, and that is actually 0.5 of a volt. Okay, so that would be 0.45, 0.4, 0.35, and so on all the way down. So what I'll do is I'll connect the voltmeter here up to the source. I'll ground this to the actual power supply, and I'll connect this to that 0.501 volts there. So I'll ground this right now, and I will connect this up to here. Now we're in the 1.5 volt range, and we're right on 0.5 of a volt, which is really good. So now I'll go down to 0.5 volts, and that needs to be adjusted. So I need to adjust the meter back till it reads right at the 5.0, and I'll do that right now. And there we go. That's done. So it says here, important notice, since the AC0 calibration control is used for setting the 0.5 volt calibration, AC0 calibration must always be performed after the 0.5 volt DC range is recalibrated. So again, we didn't use this AC0 to do this, so we really don't have to worry about that. And that is the next step anyways. So we'll go to that next step in just a moment. The next step is the AC0 calibration. So it says here, remove the probe lead from the front panel connector. So we're just basically disconnecting the probe at this point. All right. It says here, set the function switch to AC. This is the function switch. Move that over to AC. It says here, set the range switch to 1.5 volts. So I'm going to move this up to 1.5 volts. It says adjust the AC0 calibration control through the hole in the side of the cabinet so that the meter needle rests exactly at 0 on the left side of the scale. So the AC0 set is right at the bottom. It's at the very bottom hole in the cabinet here. So I'll put my insulated screwdriver in here and we'll set the 0. And there it is. So now we're right on the 0. And now we're on to the AC calibration. We're now at the AC calibration procedure for this vacuum tube voltmeter. So this AC calibration procedure you see here is the dangerous calibration procedure involving this voltmeter. So this requires you to have a 120 volt AC source to align that particular portion of the meter. Now the way that they're telling you to do it in this data sheet is from way back when, and it's a very dangerous procedure. So there's a couple of amendments that you should do if you're going to do this. Again, if you're not confident with working around high voltage AC or DC, do not do this procedure. It says here, connect the probe lead to the front panel connector. So we've already done that. This is already connected up again. So basically they're just telling you to screw the probe back on. Of course, there is no AC on the probe or anything at that time. The probe is free floating. It says set the function switch to AC. We have it set to AC. It says set the range switch to 150 volts AC, which is right here, and it's set there already. It says set the probe switch to AC ohms. Now I've done that. That's the probe switch on the actual probe, that little switch on there. You have to click it to AC ohms. And it says here, caution, you are going to use the AC power line as a voltage source for calibrating the AC voltage scales on your vacuum tube voltmeter. Use extreme care as you connect the leads and make this adjustment. Now do not do this. What you want to do is have an isolation transformer and a current limited source. Don't ever connect this voltmeter directly to the AC line. For reasons being is the negative or the common lead that's coming out of this meter, which is this black lead right here, is connected right to the case of the meter. So if you connect this up backwards, this case is live. So you must have an isolation transformer in line before you do this, and it should be current limited. So I've already got mine hooked up, and you can see that there's 120 volts AC present here right now. So I didn't want to fiddle with these wires, you know, while we're doing this video here, because I don't want to risk zapping myself. So everything is all hooked up at this point. So it says here, connect the probe tip and common lead across the 120 volt AC power line. Now I have mine connected across my isolation transformer that's current limited, and don't ever, as I say, don't ever hook this to the AC power line directly. You have to have an isolation transformer and it should be current limited. Again, do not do this unless you are confident in what you are doing. It says here, do not touch the case or the front panel of the vacuum tube voltmeter as you make the following adjustment. Adjust the AC calibration through the hole in the side of the cabinet so the meter needle indicates the exact value of the line voltage, 120 volts. So that's the second adjustment hole up here, and you need to use your insulated screwdriver. So I'll put that into the AC calibration here, and I have to adjust this until it says 120 volts. And there it is right there. That's right on 120 volts. And that completes that portion of the alignment. We're now at the final calibration procedure for this vacuum tube voltmeter, and that is the ohms adjustment. So the ohms adjustment is made with just the controls on the face of the VTVM. We're completely done with setting the potentiometers in the side. We no longer need to touch those controls at all. So it says here, note, the battery must be installed in the vacuum tube voltmeter before making this adjustment or taking resistance measurements. So what they're telling us is that we should have a fresh C-cell battery in this VTVM, and we should also make sure that those battery contacts are free from corrosion. It says here, set the function switch to positive DC volts. So now we're at positive DC volts. It says set the range switch to 1.5 volts RX1. So move this to 1.5 volts RX1. It says here, now connect the probe tip to the common lead and readjust the front panel zero control to set the meter needle at 0. So all they want us to do is short the probe again. And you'll want to also make sure that it is on AC ohms when you're doing this. So now we readjust the zero control here. Bring that right onto the 0 mark. It now says remove the connection between the probe tip and the common lead, so they're just telling us to break the short. Okay. It says here now set the function switch to ohms. Now we're in the ohms position. Adjust the front panel ohms control so the meter needle indicates full scale, the sideways 8 or the infinity symbol on the R scale. So there's the infinity symbol right there, so we need to adjust this ohms control right over here in order to bring this right to that line. So now we're right on the infinitive symbol. It says now touch the probe tip to the common lead, the needle should drop to 0, that is 0 resistance. So now when we short this out again, it should drop down to 0. Now you'll notice that we're not exactly at 0 here, and that's because we have a little bit of lead resistance in here. Now if I bring this probe to actually touch the barrel here, you'll see it drop down just a little bit more. So it kind of cancels out the resistance of this long line, but we still have the resistance of the switch and all the wiring in here and all the way through this cable here, all the way up into the connector over here. So there's a little trick that they don't really tell you. And that little trick allows you to zero out the resistance in these leads. And I'll show you that little trick right now. So what you do is you just leave this short here, and what you do is you grab this zero control and bring this needle right down to the 0 again. So now we're right on the 0. Now what you do is you break the short here, and you go up to the top of the scale, you adjust this ohms control at the end here again, and bring it right back up to the infinitive symbol. Right there. Now when I short this, it should go right back to 0 again. It goes right back to 0. And now you've effectively gotten rid of the resistance in these cables. You've nulled that out. So I have a 1.1 ohm resistor here. It says 1 ohms, but it's actually 1.1 ohms, and that's been verified on my GenRad. So I'll give you an idea of the accuracy. I'll just clip this in here, and I'll touch the resistor. And there we go, we're right at 1.1 ohms. This is 1 ohm, and that's 1.2 ohms, 1.4 ohms, 1.6 ohms, 1.8 ohms, and 2 ohms. So we're at 1.1 right there, right between the two marks. So if you need this kind of accuracy, you can zero out the leads by doing that. If you're not worried about having the low ohms that incredibly accurate, you don't need to do that extra step. So that's just one little trick that they don't tell you in the manual. So this completes the calibration procedure for this vacuum tube voltmeter. This Knight vacuum tube voltmeter is now completely aligned and restored, and I'll give you an idea of the accuracy of one of these old voltmeters. So I've got the ground cable from my voltmeter already hooked up to my power supplies, and I'm going to use this voltage divider here again, and we're going to test the 0.5 volts, the 1.5 volts, and I'll also test the 5 volt scale, and that should give you a rough idea of how accurate this meter is. So here's the probe. I have to have it on DC in order to measure DC. So what that's doing is that's putting a 1 mega ohm resistor in line with the tip here. So what we'll do is we'll zero out the 0.5 volts DC, because that's the scale we're on right now, and I've got the ground already hooked up, so I'll just touch this spring here, and that should allow me to ground the probe out enough, and then we'll just zero it up. Now I'm going for the absolute most accuracy I can here because I'm displaying this, so that's right on the 0 mark. Alright, now I'll attach the probe to a clip that's at 0.5 volts. You can see that that's right on at 0.5 volts right there. Okay, so I'll go to the next scale. I'll go to the 1.5 volt scale. Now remember again, just in case you missed that, this scale here where the 5.0 is 0.5 volts, 0.45 volts, 0.4 volts, 0.35 volts, and so on all the way down. So now we'll go to the 1.5 volt scale, and I'll re-zero the meter again just to make sure, and it's right on the 0. So now I'll test the 1.5 volts, and it should come right up to the same line again because we're on this upper scale now. And there we go. It's right on 1.5 volts. Okay, so now I'll go to the 5 volt scale here. I'll re-zero the meter again. Make sure it's zeroed. It's pretty close. I can bump it down just a little bit. All right. It's very, very close. As I say, I'm being really, really finicky. That's probably a hair's width from the 0 before, so you don't really need to do that as you're going through the scales. I'm just doing this to display the accuracy of the meter. So now this is kind of interesting. This is at 5 volts right now. Now I'll connect the 5 volt supply. And that's the 5 volt supply. Now you can see at the end, the needle's a little over the 5 volts, and I'm going, oh, maybe the scale isn't so accurate. So, I'm doubting the meter at this point. So then I hook up my new Agilient meter, and that's where the actual voltage is sitting at 5.1 volts. So again, this is accurate. And that just gives you a rough idea. I showed you the 1 ohm resistor in the last shot, so we really don't need to go through the ohms range, and the AC is just as accurate as what you see here. So there you have it. This very old vacuum tube voltmeter is, I would say, extremely accurate. Well, I hope you enjoyed following along through the restoration process of this Knight vacuum tube voltmeter. If you did, give it a big thumbs up and hang around, and there'll be quite a few more restoration videos just like this. See you next time.